Okay, so in today's lecture, we're going to cover sections 5.7 and 5.8. And these sections introduce the inverse trig functions together with how to take derivatives of them and how to integrate them. Now, when we learned about inverse functions, there was a characterization theorem that we gave, right? So what was that theorem? It says there's something like so a function f of x has an inverse if and only if it is 1-to-1. Okay, so that was a characterization that we had of a function having an inverse. Now, clearly, the trig functions are not 1-to-1. So if I just look at the graph of sine, for example, so what does this look like? Okay, so, or the graph of maybe, so what's sine's value at 0? Kind of refresh your memories if you can. Sine of 0 is what?
1.
1, right? So it's like right there. And then what's sine's value at pi over 2?
0.
Right. So maybe like pi over 2 is like over here or something. What's sine's value at pi?
-1.
Right. So it's all the way down here. So the sine function looks something like this, right? Now, this function, just by looking at the graph of it, is clear. Oh, that is awful looking. Sorry. Just saw that on my screen that it is not low enough. So just by looking at the graph, you can see that it's not 1-to-1. It doesn't pass the horizontal line test, right? Drawing a horizontal line, it's going to intersect the graph in several places. And okay, so that would mean that it doesn't have an inverse by this theorem. However, if we restrict the domain of this function to be some integral, then we can make this function 1-to-1 on a restricted domain. So, for example, if we restrict the domain from maybe here to there, so like from 0 to pi, then the graph of the function looks like this, and that would be a 1-to-1 function. So one option for the domain would be from 0 to pi. Okay. And by doing that, then on that interval 0 to pi, that function is going to have an inverse. And this works with all of the trig functions. Okay. So, and that's how we're going to define them. So, this is just a mess of a thing for me to write down, but so we define these as follows. So we're going to say the arcsine is the inverse function of sine. And arcsine, if and only if sine y equals to x with domain -1, 1, and range -pi/2 is near equal y, is equal to pi/2. So this is the definition of the inverse function for sine. This is what we call it, the arc sine. Now, okay, let me make sure that this makes sense. Let me check something real fast. It looks a little bit off. Oh, no wonder. Who told me it was 1? This is the cosine function. That's what happened. So let me go ahead and I'll tell you why it wasn't making sense in a moment. So let me write down the arc cosine function. Someone should have said something to me. This is domain -1 less than or equal to x less than or equal to 1, and range 0 less than or equal to y less than or equal to. Okay, so I knew that I had the wrong something was off when I looked at the range of the arc sine function. And when I looked at the range and I looked at that graph, something was not making sense to me. And it was that the range of the arc sine is the domain of the sine, where it's 1 to 1. So when you look at inverse functions, they interchange range and domain. So when I looked at that as the range of that function, I looked at the graph and I looked at what -pi to pi would have been. It would have been here, and that would have not been 1 to 1. So I immediately knew something was up. Does that make sense? Right? You can always check. That's what's nice about mathematics. You can always verify things if you think about them. So I knew that was off, and then I started thinking, well, why is it off? It's off because the sine function is not this. It looks like this. Right? So then everything makes sense. -pi to -pi/2 to pi/2, this interval here, that would be a 1 to 1 function. Okay. For cosine, -pi/2 to pi/2, that would not be a 1 to 1 function. So that's how I caught my mistake. Okay. And the domain for these is -1 to 1 because the range for the original functions is between 1 and -1. So again, there's this interplay between domain and range and how they interchange with your inverse functions. Okay, so then let's go ahead and write the next one. Our tan, if and only if tangent y is equal to x, with domain -infinity less than or equal to x less than or equal to infinity, and range what is it, -pi/2 to pi/2, not including, because those are the vertical asymptotes of tangent, but not including. Yeah. And the arc cotangent, arc secant, and arc cosecant, they're all defined in similar manners, where you look at the original function and you restrict its domain. So this is the restrictions in the domain for the original function. Okay. you do that so that you can have a one-to-one function, which means you have an inverse, which means that these are appropriately defined. And there's also, we could have, for example, for cosine, we could have chose like pi to 3 pi or whatever, but it's mathematically convenient that we choose the restricted domains for the original functions to include the value 0. So for all definitions, you'll see that 0 is always a possibility in the interval. Okay, so it might seem like, why would we do this? Like, well, because these functions are inverses of the trig functions, if we have a trig function generating some number and we want to know the angle that made that number in the function, then we can take the arc, cosine, arc, tan, arc, whatever, to find out that angle. So, for example, maybe we have that, well, we'll get there in a moment. Let's just show how these things work. So our tangent, 2x minus 3, is equal to pi over 4. So we can solve this equation for x now that we know the definition of our tangent. Also, well, we just take the tangent on both sides of this. And now, tangent of arctangent just gives you the argument, which happens to be 2x minus 3 in this case. And that's because they are inverses of each other. And then tangent of pi over 4 is just 1. And then we solve for x. So x would be 2. Okay? Okay, so let's now look to see how we can use arc or trig inverse functions to study triangles. So, another example. So given y equals to arc sine x, where 0 is strictly less than y, which is strictly less than pi over 2, find cosine of y. This seems like a very strange question. Like, you look at it and it's not clear, like, how would you ever find out what that is, right? This is where you have to draw a picture. So, solution. Draw yourself a right triangle. Okay. So then, let this be the angle y, right? And if we know the sides of this triangle, so if we're able to find out that, and that, in particular, this one and that one, then we can determine what cosine y must be. Okay, so notice now that by definition, arc sine, so y equals arc sine of x, if and only if what? Sine of y is equal to x, right? That's just the definition of the inverse. But this is opposite over the hypotenuse, right? So opposite over the hypotenuse is x. So we know that. So sine of y is equal to x means that x over 1, right? Or opposite over hypotenuse. But once we know that, we know that this is going to be the square root of, so that squared plus that squared is equal to that squared. So that means that 1 minus x squared is equal to this thing here. Okay. So what does that mean about cosine? Well, cosine is that of that, right? So cosine y is going to be equal to root 1 minus x squared. Okay. So you put in a given x, which gives you out a y, and then you can immediately determine what cosine will be. Okay, let's look at an actual numerical value or problem. So given y is equal to arcsecant, and that's just the inverse of the secant function. So arcsecant of root 5 over 2, find tangent y. Okay, so now we're going to have an actual value. Well, again, it's going to really help to draw yourself a right triangle to figure this out. So a triangle, make this y. Okay. So now, what do we know about this definition here? So y arcsecant of root 5 over 2. Well, that's true if and only if the secant of y is equal to that. So you just take the secant on both sides. And again, this is because they're inverses of each other. Okay, so secant y is equal to that. This means that, well, I always think of it as, so 1 over cosine y is equal to this. Which means it's basically cosine y is the reciprocal of this value. So adjacent hypotenuse, so this would be 2 root 5. Sorry. Okay. One second. No, that's fine. And, okay, so now in order to find tangent, we just need to know what that is over here. So to find out that, we just use Pythagorean theorem here. So what is this value? Well, I know that x squared plus 2 squared is equal to root 5 squared, which means that x squared is equal to 5 minus 4. So that means that x is equal to 1. So then once I know that x is equal to 1, tangent y must be equal to 1 over 2. And then that's it. Okay, but this was all basically review from a pre-calculus type of course. Now it's time to get to the actual calculus. Okay, so here,
let me talk to my mom again. She was gonna talk to my dad, but let me call you back. Give me 1 second.
So let you be.
Yeah, let me talk to them.
Someone's mic is on. Okay, so let u be a differentiable function of u, or a function of x. I'm sorry. Okay, so there's a bunch of these. There's going to be a formula for the derivative of each of these trig functions or inverse trig functions. So so the derivative of arc sine u, that's equal to u prime over root 1 minus u squared. Part B, arc cosine now. It's just the negative of this. The u prime over root 1 minus u squared. And then part C, derivative of arctan is going to be u prime over 1 plus u. Okay, and I'm going to try to squeeze them in because we're going to need them on the board for the rest of the lecture. Part D, so derivative of our cosecant barely going to fit. Negative u prime over absolute value of u times the square root of u squared minus 1. And then part C. Let me just write these down. Secant u. It's just the positive of this. Oh no, CTE actually. Arc cotangent, so cotangent u, negative u prime over 1 plus u squared. Okay, so these are the standard, this is the table, I guess, that you'll want to have whenever you take your exam. You're probably going to want that list from at the beginning of your textbook, that table of integrals and derivatives. You're probably going to want that handy when you take your first exam. Now, let's argue why one of these is true. Maybe the first one, part A. So proof of part A. So we want to know the derivative of arc sine. And so arc sine of u is equal to, say, y if and only if u is equal to sine y, right? That's just the definition of being an inverse. Now, we're assuming that u is a differentiable function of x. So that means that du dx is equal to, well, the derivative of this with respect to x, well, we use the chain rule, and we see that that's going to be cosine y times dy dx. Okay, so now I'm going to write du dx as u prime, and see that if I divide both sides by cosine y, I get that u prime over cosine y is equal to dy dx. Now, why did I do this? Why did I'm trying to like show that this formula here holds. Well, if this is equal to y, the derivative of y is right here. So we found it. However, this is still an implicit form, and I need to write everything in terms of u on this side. So how can I do that? Well, we know that sine squared y plus cosine squared y is equal to 1. I'm assuming that all of you would remember that. And then if we solve for cosine y, we get that cosine y is equal to the square root of 1 minus sine squared y, right? So now if I kind of rewrite this whole thing here, I get that dy dx is equal to u prime over cosine y, which is really this. So that's 1 minus sine squared y. But then sine y is equal to u. So this is just u squared. So finally we get that dy dx is equal to u prime all over 1 minus u squared. And that completes the proof of part A. Well, derivation really. Okay, so that's why these formulas look the way they do. This identity right here is making that, it's making that, that and that. And it turns out that that form is going to be very useful. And one of the biggest use cases that I've encountered is that these forms pop up a lot when you're trying to take integrals, and the antiderivative of something that looks like this is that. So you know how to integrate these things when they have this type of form. And, okay, so let's just go ahead and look at some examples actually computing these things. So I don't know, derivative with respect to x of arc sine of 2x. Okay, so here u is going to be 2x, right? So just you might want to make note of that when you're doing these problems to really write down what u is. U is 2x. When we're looking at the derivative of arc sine, so this is going to be u prime over the square root of 1 minus u squared. So this would be u prime. So what is u prime? The derivative of u, which is 2. So u prime all over 1, the square root of 1 minus u squared. So it's all of that squared, so it would be 4x squared. Okay. So here's another example. Let me just make sure that I'm not missing any questions. Yeah. Let's look at the derivative with respect to x of our tangent of 3x squared. Okay, well, there's your u. And it looks like we're going to need to know the derivative of u. So u prime is going to be 6x. And then just plug in. So the 6x all over 1 plus 3x squared. That's it. So really taking derivatives of these inverse trig functions is really easy. You just need this table next to you. Okay. But let's do a more interesting example other than just computing the derivative. Okay, so determine the extrema and points of inflection for y is equal to arctan of x all squared. Okay, so basically, if we're going to determine the extrema, we need to find the critical numbers and then determine if they're minimum or maximums for this function. And then the points of inflection on the graph are where the second derivative is equal to 0. Okay, so there's going to be a bunch of parts to this, I'm assuming. Okay, so we need the derivative for sure. So dy dx. So if we use the chain rule, it's going to be 2 times arctan x. And then times the derivative of the inside, which is, so this is your u now, so it's going to be the derivative of x, which is 1 over 1 plus x. Okay. Okay. So so in order to find the critical points, when is the derivative equal to 0? Well, it's definitely going to depend on when arctan is 0. So if we look back to the domain of arctan, which was, the domain is all real numbers. This is going to be 0 at what? Well, it's going to be 0 at x equals to 0. In fact, that'll be something for you to think about. So this is like scratch work. There's going to be a lot of parts of this problem, but so in order to figure that out, we want to know when that's the case. Well, it's the case that if you take the tangent on both sides of this, you get that x is going to be equal to tan of 0, and tangent of 0 is 0. Right? So, in fact, that's the only place where it's going to be there. The only place where tangent is 0 is x equals 0, so that is the only number you can plug in to make the derivative equal to 0. So this is, and this is defined everywhere. Is the critical number. Is a critical number. Okay. That's the problem. This u should be u squared. I was about to say, I thought this thing only had one critical number, but if that didn't have a square on it, then -1 would also be a critical number, and that was throwing off how I envisioned the graph. So yeah, the actual formula for the derivative of the tangent is u prime over 1 plus u squared. Okay, so sorry about that. And then in that case, yes, x equals 0 is the only critical number. Because even if that's a -1, squared is still positive. Okay, so now, is this going to be a relative minimum or relative maximum for the original function? I'll leave that as something you can try to figure out on your own. I'm really concerned because many of you didn't take Cal 1 with me. I emphasize these critical numbers, the first derivative test, these things a lot. So I hope that you go back in the textbook and you read about first derivative test, second derivative test to determine if critical numbers yield relative min, relative maximums. Okay, so that'll be an extrema. Once you determine that, it is going to be a minimum. This is a relative minimum. And now we need to determine the points of inflection, which means we need the second derivative. Okay, so that's going to be messy looking. So if we take the derivative of this, so this is going to be derivative of that times that plus the derivative of this times that. So it's not going to look too great. So derivative of this is 1 over 1 plus x squared. And that one's not too bad. Plus the derivative of this times that. So I'm going to come over here and do that on the side. We'll find out what the derivative of that thing is. So one over x squared. The same thing as taking the derivative of 1 squared minus 1. Negative 1 plus x squared to the power minus 2. Oh no, wait a minute, sorry. -1, subtract, and then derivative of the inside to be 2x. So this will be negative 2x over 1 plus x squared all squared. Okay, so this will be 2 r 10x times that plus x squared all squared. All right, so what all do we have? This can look a lot nicer. I can make that look nicer. So the second derivative is going to be 2 over 1 plus x squared all squared minus 4x arctan x all over 1 plus x squared all squared. Oh, they have a common denominator. That's nice. So then this would be 2 minus 4x arctan x all over 1 plus x squared all squared. Okay, so we need to determine when this is equal to 0 to find the points of inflection. Now, basically, in order for this to be 0, the numerator needs to be 0. So what do we want? We want this to equal 2. If this equals 2, then we're done. Or I might just make it look nicer. I factor out a 2, 1 minus 2x arctan x all over 1 plus x squared all squared. We want this to be equal to 0, or we want this to equal 1. Same thing, right? So we want 2x arctan x to equal 1. Okay. So how can we determine this? Actually, let's see. For x arctan x equal a half. What could that be? Well, how did the textbook do this? Let's see. Oh, interesting. The textbook doesn't solve it analytically. They solve it numerically using Newton's method. In the chat, tell me if any of you have ever heard of Newton's method. I'm not sure if your Cal 1 professors taught you Newton's method. Oh no. It looks like y'all have not seen Newton's method. Anyone else? Okay. We will come back to this. I need to finish the inverse trig stuff. But especially since there's so many CS majors, I'm going to teach you Newton's method after we do this. So we'll come back to finding the solution to this. Okay, I need to get to integration. But we found the critical number. It's going to be relative minimum by the first derivative test. And then we made our way down to here. But looking for the points of inflection by setting the second derivative equal to 0, and then we made it right there, but apparently we can't solve it unless we know Newton's method. So that's where we stopped on this problem. Okay. So now let's look to integration. Now notice that these two derivatives are basically the same. Okay. And that these two derivatives are basically the same. They differ by a sign, right? That's positive, negative, that's negative, that's positive, but they're the same. They're not the same, but they differ by a -1. And the same thing happens for arctan and arccotan. Because of that, the table of integrals is reduced to half the number of derivatives. Okay, because you can just take out the -1 as in front of the integrand if there was a difference in the sign. So I guess we can lump this into the following table. So if a is greater than 0, then it's like 1. The integral of du over root a squared minus u squared. This is just, well, we're looking at the antiderivative of this. This looks like that, right? Du over 1 minus u squared. Except the difference is now there's an a, but we can account for that by putting it as follows. This is arc sine u over a plus c. And then 2 du over a squared plus u squared is equal to 1 over a arctan u over a plus c. Okay. And then finally, 3, we have du over u times root u squared minus a squared. This is going to be equal to 1 over a arc secant u over a, the absolute value of u over a plus c. Okay, so that's your table of integrals. Now, you're not going to like these. And the reason why I say that is because now when you take integrals, you're going to have a bunch of different options, and all the techniques that you know to get to one of those options are valid, and you can end up like going down rabbit holes for not the right one. And you're only going to see that through doing the homework problems that I'm going to assign this time, and I'm going to pick up. Okay, so let's start simple. Okay, let's look at the integral of dx over 2 plus 9x squared. Okay. Now, when you look at that thing, and whenever you see a form that's anything similar to one of those, immediately think to the inverse trig functions. Of these, oh, it kind of looks like this, right? So, but it's not exactly that. Can I write it like that? And the answer is yes. you can write this as that plus 3x all squared. So now it looks much similar to this guy as a number squared plus a function of x squared. So now u is going to be equal to 3x. So then du is equal to 3 dx. Okay, so 1/3 of du is equal to dx. So now we substitute back in, we can take the 1/3 out in front of the integrand, and then we have du over √2 all squared plus 3x, oh no, sorry, u squared. Now it matches perfectly with that, and I can write it out as 1/3 times 1/a. Maybe I'll just write that. A is equal to √2, right? So 1/a times arctan of u over a. And what's u? What's that? And then don't forget your constant of integration. But that's probably not what it looks like in the book. It honestly probably looks like you rationalize that and it would be √2 over 6 arctan. Yeah, it'd probably be, I guess they would rationalize it maybe. 3x √2 over 2. Let's see. It might have a form that looks like that. If it doesn't like that, it looks something like that. Just remember, the textbooks like to rationalize their answers. Okay, but this is a correct answer, even if it's not the one that appears in the book. Okay, so let's do another one. So maybe okay. I'm going to go ahead and pause the video. Yeah, I'm going to pause it and let you work on this one for a second. Okay, so let's go ahead and work this one out. So immediately I would notice that I can rewrite this indefinite integral as follows. This would be 2x all squared and then minus 3 squared. So here I see immediately that it matches up with the third integral down here, the arcsecant one. So then in that formula, a would be 3, and then u looks like it would be 2x. Now I just need to take the derivative of u and make it look exactly like this one. So du is going to be 2 dx. So 1/2 of du is equal to dx. So now if I substitute in for dx and for u, I get I'll show you. I'll take out that 1/2 and then write du right here. And then I need to rewrite that x, right? I need there to be u right there. So I look up here and I say, oh, I see that u over 2 is equal to x. So that's what I'm going to replace it with. And then times root u squared minus 3 squared. So dividing by a half is the same thing as multiplying by 2. And if I take that 2 out, 2 times that half goes away. So now we have everything that we need. And this will be 1 over a, but what's in my a? It's 3 times arcsecant. Absolute value of u all over a and then plus c. Okay. All right. Maybe one more, 2 more, maybe. All right, so here we have the integral of x plus 2 all over root 4 minus x squared dx. All right, so with this one, we have sort of a problem. That plus 2 right there, and the x in the numerator actually is the problem. The sum is going to be difficult to deal with because I don't see how exactly if we did u substitution. So if u was x, right, du is dx, and then we have that extra x up there. And that's the problem because none of these have u in the numerator. But what we can do is write this as a sum of integrals. Right? You can always do this. And then see if we can figure this out. So, I'm gonna run out of room here. X 2 as the integral dx over 4 minus x squared. Okay, y'all read that?
Yeah, I can see it.
Okay, so now I see this looks good. And what about this side over here? How can we deal with that one? And we have every integration technique that we need, right? In fact, this is, yeah, we're going to just have to use normal u substitution here. And then here, we're gonna have to do arc sine. Right, so we'll wait on this one, we'll do that, and then we'll compute this on the side. So this would be, so A here is 2, and U is X, so this would be arc sine. So U is just X, A is 2, plus C1, constant for this interval here. And then here, running out of room. So if U is equal to X squared, then, or negative X squared maybe, then du is equal to negative 2x dx. Actually, let me rewrite it in the ratio form. So x dx all over root 4 minus x squared. Okay, so now I see that negative 1/2 du is equal to x dx. Okay, so I take out that negative 1/2, x dx is du all over root 4 plus u. Okay. Hate not having big teaching boards. Like, this is annoying to run out of room.
So you would change that 4 to 2 squared?
Oh, it would be way easier to just let u be the whole thing in the bottom, actually. Do you see, like if u was equal to 4 plus u, if u is equal to 4 minus x squared, then du is still equal to negative 2x dx. You see that, right? Because that's just a constant. So then this becomes really simple, right? Negative 1/2 du is equal to x dx, even when u is equal to that whole thing. So if I take the negative 1/2 out, then I have du over root u. And we know how to integrate that for sure, right? That's like taking the integral of u to the negative 1/2 u, and that's just the power rule, right? You add 1 to that exponent, right? So 1 plus the negative 1/2 is just 1/2, and then you divide by 1/2. Divided by 1/2 is the same thing as 2. So then this will be negative 1/2 times 2 u to the power 1/2. And then we have all this stuff over here as well. I can combine the constants of integration now. But then what is u? U is that. So then we're done. This would be negative 4 minus x squared. That's a square in there. All to the power of 1/2, because that 2 times negative 1/2 just leaves a negative. and then there. That will be the end of it. I think your book uses square root or something, but this is the answer. Square root is the same thing as car 1/2, so all of this. And as you can see, you're going to have a fun time with the homework. These integrals are basically combining all the knowledge you know about integration from Cal 1 together with seeking out these rules, and you have to know when to use one or the other. All right. So, I guess one last one. And you're going to need a lot of paper, for sure. Definitely a lot of paper to do these. So there is a specific technique for making a difference of squares or a sum of squares. So even though this doesn't look like one of these right now, you can add and subtract a number to make it look nice. And by that I mean we can complete the square, which you probably haven't done since an algebra course. But basically, if you have, I need more room, but so if you have something that looks like this, which that looks like that, I'm sorry. You can take half of B and add and subtract it. That's a B, right there, B. So plus B over 2 squared minus B over 2 squared, and you have your plus C there. If you have something like this, you can now write this as, what is the terminology? I just call it completing the square. Your book might use something, yeah, no, your book uses the same thing. They just call it completing the square, I think. Well, when you do this, you can factor. That's the whole point of it. In particular, this piece right here, you can factor as x plus b over 2 all squared. And then you have the other bits left over, b over 2 squared. Let's see. But basically, you can get square, square. And in each of these problems, you're going to want squares, right? So let's see what happens when we complete the square of this. So here b is -4, so we would add and subtract half of that squared. So plus -4 divided by 2 is -2. So we have to add and subtract it in order for it to stay the same. Okay. Okay. So now that's going to factor, right? Okay, so this is going to factor 2. So this is the key part right here. That's going to factor into x minus 2 squared. And then this becomes 4, but it's a -4 and a 7, so this would be plus 3. Okay, now it's looking better. It looks like we can rewrite it to look like the arctangent version that we want. So say root 3 all squared plus x minus 2 all squared. And now x minus 2 is your function u. So if u is equal to x minus 2, then du is equal to dx. So it works out nicely right here. U still the root 3 squared plus u squared. And that's going to be 1 over root 3 arctan of u, which is x minus 2 all over a, root 3. Let's see. Okay. All right. There are. I'll go ahead and stop the recording there, actually.